Hey, this is the first in the Think Like an Expert series for Honors Physics at Oakmont High School. I'm Mr. Worden. Welcome to Motion Graphs. All right, first thing we want to do about motion graphs is realize that it breaks down into a couple simple patterns. First pattern we've got is when an object isn't moving. How can you tell? Well, at the first point in time, I check and the object's here. A little bit later on, I check again. The object is in the same location. I've got my distance or location on the y-axis. So what you're looking at on the distance graph is a flat line straight across. No matter what time we check, it's in the same spot. If it's not moving, then you automatically know that the velocity of this is 0. It's got no speed. It's not going anywhere. And as long as that's not changing, we know that we're also not accelerating. So that's the simplest of the three patterns. A little bit more complicated pattern is when the velocity is constant, as in we're cruising along the freeway at the same speed. We're always walking 4 miles an hour, or we're pedaling our bike at the same rate. So here, when your velocity is the same throughout time, what's going to happen is, after a little while, you'll have changed distance. After a little while more, you'll have changed distance again, that same amount. Then after a little while more, you'll have changed again that same amount. What I'm sketching out with the mouse cursor is rise over run. What we're going to keep having is every time interval, the distance goes up or down by whatever the velocity is. Now, if the velocity is constant, if we're going the same speed the whole time, then we're not accelerating. What acceleration does is changes the speed. Now, when we are accelerating, that's when our speed will be showing that linear pattern, where every so often the speed is changed by the same amount. And then you wait the same amount of time, change the same amount of speed again. So our speed or velocity is following a linear pattern when you are accelerating. What this does to displacement is it actually makes a quadratic pattern, something with the x squared in it, if you're thinking in terms of math terms. So you're going to look for a curve on the distance graph in cases where you're accelerating. We'll talk more about this relationship here later too. Now, how does this relate to math? Well, here's our master distance equation right over here. This is final position, this is initial position, initial velocity, time, acceleration, and time again, this time squared. What happens if I have no velocity and I have no acceleration? If these values are both 0, then the only thing going on is that my new position is the same as my old position. So this is the only term that matters when you're not moving. Where were you? If you're not moving, that's where you still will be. So when this term is active is when this pattern emerges. What about when we have velocity? Oh, when we have velocity, that's this graph right here. Well, what we're looking at then is that our position is changing as a function of time. So I like to think about this, because of math classes, as y equals mx plus b. If we look at this part, this is the linear component in that. That's why we're getting a line right here. Lastly, when I have acceleration, that's when we have a squared function. I mentioned earlier that we're looking at quadratic or parabolic curves here, however you want to talk about it, second order functions. That's because this is kind of like x. See? Time is on x-axis. So I think of this as y equals ax squared plus bx plus c. I think of this as kind of the quadratic equation written kind of backwards. And that's why we're seeing quadratic patterns here. Okay, looking down one graph, here is our velocity equation. If we don't have any velocity and we don't have any acceleration, this has to be 0. If we do have some velocity, but we're not accelerating, then the new velocity is the same as the old velocity. Here we're just cruising along, it's the same the whole time. So when this term is active is when we have velocity, but it's not changing, it's constant. Finally, if we are accelerating, then over each time interval, that velocity is going up or down somehow. In this case, we're adding to velocity over time. As it goes up, this is what's driving the linear pattern. So I like to see this as y equals mx plus b. All right, now, those were the general patterns, but it's not the only way it can happen. Here we're looking at 4 different distance graphs, or displacement graphs. First thing you want to notice about these is these are all curved. Which pattern does this go with? This pattern goes with when we're accelerating. So having acceleration causes displacement graphs to curve. Okay, how are they curving? Let's look at this one on the top right first. Here, over time, we haven't changed our position very much. That tells me that when this is shallow, it's not a very steep slope, that we're moving slowly. Over here, over very little amounts of time, we changed our position a lot. That's going fast. So this is going from slow to fast. You can tell because the distance graph is showing shallow, very little change in position, to steep, a huge change in position. Now, are we adding to distance or subtracting from distance? Well, in general, this is an uphill graph. So our distance is getting bigger. So if I had to assign the velocity to be positive or negative, in this case, I would say the velocity is adding to our position as we're climbing up the distance axis. So this goes with a positive velocity. Okay, now we mentioned that it's speeding up. In order to speed up with a positive velocity, we also need a positive acceleration. So this is a case where the velocity and acceleration are both positive. When those two ideas match up in terms of positive or negative sign, that's when you're getting faster. Let's look at a weird, similar example. This graph right here on the bottom right, here we've got a flat area at first, and later it gets steeper. That tells me over time, this is changing very little in terms of position. We're going slow, in other words. Here, we're changing in a little bit of time a huge distance. That means we're going fast. So again, shallow to steep tells me we're getting faster. But here's what's different about this graph. In this graph, we're decreasing our displacement. We're taking away from the distance they've traveled. Well, that's kind of a weird way of saying it. We should stick with a vector term called displacement. Our position is coming down. Okay, so what that means is the velocity is negative. We have to have a negative speed. We're decreasing where the object is compared to where we're looking at. It's coming back towards us. And what this means is if we're speeding up and the velocity is negative, we need the acceleration to match up with the velocity so that they work together to keep making it faster. So if this is a negative velocity, it must also be a negative acceleration. Okay, let's look at this top left one now. This one, steep to shallow, hopefully you guys are starting to get the hang of this. Steep to shallow means fast to slow. So this is a slowing down situation. And because the displacement is coming down, I can tell this is a negative velocity. In the case of wanting to slow something down, you want your acceleration pointed the opposite way of the velocity. So in this case, if the velocity is negative, then the acceleration should be positive. And at first this seems contradictory. A positive acceleration, most people would say that that's speeding up. When we're thinking in terms of vectors though, we need to think, is the overall size of the velocity, which we call the speed, is the speed going up or down? In this case, if we're slowing down, we need to be doing the opposite of whatever the velocity is. And since this is a negative velocity, we must have a positive acceleration to start to cancel it out and get rid of it. Bring it towards zero. Zero is when an object's stationary. That's when you'll see these lines go totally flat, like you did in the previous slide. Same thing here. We're going from fast to slow. We're slowing down. The velocity in general is adding to displacement. It must be a positive velocity. If we want to slow that down, then our acceleration needs to be opposite that, so the acceleration must be negative. So here's a quick recap. And so it's important to start to think about which way do things curve. You can think it through every single time. One of the best things you can always do too is consider when displacement graphs are flat, you're going slow, or even stationary if it's totally flat. When they're steeper, that's when you're moving faster. That's in general speed though. You also want to consider, are we adding to or subtracting from displacement to know whether the velocity is not just big or small, but also positive or negative. One thing that sometimes helps people is to think of the U-shaped curves as acceleration being positive and n goes with negative. So n-shaped curves go with negative accelerations. I don't know if that mnemonic helps or not. If it does, awesome. All right, let's start to problem solve some stuff. Oh, looks like my animation's not quite working. All right, well, here we go. We got a velocity graph. Is this velocity positive or negative? Oh, hey, it's above the x-axis. This is positive. What I expect to see on the displacement graph above it is that the distance is increasing. And because this is a constant, I expect to see a line. Oh, before we keep going, one thing to do is when you see a graph that has two different sections, or maybe even 3 or 4 sections, to put a dotted line through all 3 graphs so that you can tell when the time gets to a certain spot here that it matches up with that spot, that it matches up with that spot. All 3 of these graphs can shift patterns at the same time, and that dotted line is really helpful to be able to see that and then graph them together and graph them accurately. So there's that first line we talked about. Velocity was positive, displacement goes up. Here, velocity is negative. I'm expecting to see displacement come back down. And again, because this is a constant pattern here, I'm expecting to see a linear pattern here. Yep, there we go. Meanwhile, did our velocity change? Were we accelerating? No, at first it was some positive number. Later it's the same positive number. Later it's the same positive number. We're not changing speed. In other words, we're not accelerating over that interval. So I expect to see 0 there. Same thing across this interval right here. Anywhere across this interval, we're not accelerating. It's the same negative velocity the whole time. But you might ask, what about this jump right here? This is a discontinuity in the graph. Jumping from here down to here, something crazy must have happened over a very short time frame. What you're going to see when you graph these in real life is a really sharp spike right where you're trying to make that jump. Can call those an impulse. Those are often involved in bad collisions. Usually you try to minimize those spikes to get a nice smooth travel of whatever kind. All right, looking at this one. We've got, starting out, an acceleration graph. The acceleration is positive the whole time. Are we adding to or subtracting from velocity? Well, positive acceleration, we're going to be increasing the velocity. Now, over this first time interval, oh, yep, there we go. Increasing velocity, linear pattern. Over this first time interval, what's going to happen? Oh, sorry, animation's out of order. Here we go. So what we're going to look at is why does a linear pattern here result in a curved pattern here? And we're going to do this without referring to any kind of calculus. We're just going to look at areas. So take a look at the area of this triangle right here. It's pretty small. If I go the next time interval over to this spot right here, this area is bigger. And if I do that same thing again, I've got an even bigger area. Why is this significant? Well, velocity is measured in meters per second. Time is measured in seconds. When I multiply meters per second times seconds, the seconds on the bottom and on the top cancel, and I'm left with meters. What is distance graphed in? Meters. So what that's telling me is the area under the curve has something to do with the way the distances are changing over time. So by having a little area here, it tells me that the distance didn't move much. Over the next time interval, I've got a medium area. From here to here, we have a medium amount of change. Then we have an even bigger area. From here to here, we had an even bigger change, and so forth. So as these kind of get bigger in terms of area under the curve, it's having an impact on the change in the graph above it. All right, let's take a look at a different perspective here. Now we're going to be working down a graph. Right here, what's the slope? Right at this spot, it's basically flat. That tells me that over time, right at the beginning, we're not changing position. We've got a velocity of 0. Let's go to the opposite side of the graph, right over here. What's the slope right here? It's really steep downhill. That tells me there's a big negative value for the slope here. So I'm going to go ahead and put a dot right there at a big negative value. And this curved pattern, just like before, is going to correspond with a linear graph, a simpler pattern on the graph beneath it. So I'm going to connect those lines. Okay, now what's the slope right here? Some negative constant value, right? What's the slope right here? The same negative constant value. The slope hasn't changed. How about right here? Same deal. Throughout this graph, we have the same negative slope What that tells me is that the answer on the acceleration graph is going to continue to be that same negative value there. So what you can do, what we're trying to identify, is that you can use area under the curve. That's a calculus term, don't worry about it. It doesn't have to be a curve. It just means we can use these areas to see how much the graph above is changing. We can use slopes to see the answer to the graph below. If we were in calculus, we'd be calling these integrals and derivatives. All right, let's do some more problems. Steep to shallow. I'm going fast to slow. I have a big velocity at the beginning. I end up with no velocity later on. Also, are we adding to or subtracting from distance? Oh, we're adding the distance. This is an uphill graph. That means that my velocity is going to start out as a positive value, and it's going to come down until we're stationary. Okay, our velocity is continually getting taken away from. We're coming downhill. This is a negative slope. 3 different ways of saying that our acceleration values need to be negative. All right, let's look at this one. Hey, I noticed that there's one thing going on here, and there's a different thing going on here. Probably the first thing I should do is put in one of those dotted lines to separate out the sections. That way I can solve this one piece at a time. I don't have to think about both things simultaneously. It's too complicated. Okay, are we moving? Well, no, my position's not changing. I'm at the same spot now as here. Okay, so we're not moving. It's just zero velocity throughout. And our velocity is obviously not changed, so we must also not be accelerating. Ooh, whoa, skipped ahead, my bad. Let's do this other section. Stationary to fast, and adding to our distance. That's telling me stationary, zero velocity, up to a big positive value. Yep, there's our line. Okay, right here, no acceleration. Right here, yep, we're adding to velocity very consistently. We're going to have a constant positive value. Also, what's the slope of this? Oh yeah, a positive number. All right, this one right over here. 2-section graph, put in your dotted line. Next step. This pattern, I'm starting to recognize goes with a curve up here. Question is, which curve does it go with? Okay, we're stationary at first, that's going to be flat. Later, we're going faster, that's going to be steeper. And we're in the positive direction, we're above the axes there. These are positive velocity values, so we're going to be going up the graph. So I need to go from shallow to steep up the graph. I'm predicting a curve like that. Oh, whoa, what? Oh, I guess we're doing acceleration first. Okay, so acceleration, yep, we keep adding to our velocity. Rise over run, constant, cool. Right over here, we're going to have no acceleration at all. Now, right here, we've got a discontinuity, a break in the graph. Something crazy happened there. It was going really fast, and very suddenly, they switched to a much slower speed. We dropped the velocity. I'm predicting a downward spike on the acceleration graph. A very abrupt but huge acceleration. Yep, there we go. Okay, now back to this. An uphill curve is what we predicted before. How about now? Over time, we've added this much area, then we add the same amount of area, then we add the same amount of area. So this is going up by a constant increment. I'm expecting a line. Is the line going to match the slope of the thing that came before it? No, we've got a discontinuity here. These graphs will still be connected. You can't teleport. You can't jump from one location to another location. But you can really quickly change how your slope is showing up to reflect that change in velocity. So I'm expecting a shallow uphill line after this. Oh, there we go. So here's a recap of the equations. We got a velocity equation. We've got a distance or displacement equation. This part makes the graph flat. This part makes it linear. This part makes it curved. That's for the distance graphs or displacement graphs. On the velocity graphs, we don't have anything that's going to be curving them at this level of physics. But we can have flat ones or linear ones. Also, if everything's zero, then obviously these are zero. Also, we've been talking a lot about positives and negatives. That's a direction. That means that we're using vectors to think about this, where direction does matter, not just how much, which is the magnitude, but also which way is it pointed. So that's why sometimes I'm switching back and forth between the words speed and velocity, or distance and displacement. I'm trying to be a little bit clear about, do I mean with the direction, or do I just want to know how much or how fast? All right, we're not going to finish this word problem, but let's take a look at how we might actually set up a quantitative graph. We've got these two equations. We've got a word problem where we've got, it looks like a rabbit and a dog. Okay, so there's two different objects we're going to be tracking. Let's track them separately. So I set up a data table for a rabbit and set up a data table for the dog. All of these graphs are a function of time. That's why I put t in the first column. So depending on the time, we'll get different answers for distance, velocity, acceleration, or displacement, velocity, acceleration. What I can do is, from the word problem, my goal is to fill in the initial conditions. So initially, the rabbit was going 5 meters per second. I would take that number and put it right here in the velocity initially. And it has a 20-meter head start. I would put that down as the initial displacement. The rabbit is not accelerating. It doesn't mention anything like that. So I would put a 0 here. These values are what I would plug into this equation. I would simplify it then, and only then later would I start plugging in different time values like 5 or 10. And when I put in 5, I could calculate the distance that goes right here. When I put in 10, same thing, I'd be calculating the distance that goes here. Notice that on the right half of this equation, I'm not changing values halfway through the word problem. I'm keeping my initial conditions, and I'm changing time. These are functions of time. If I want to calculate these velocities, I'm going to do the same process, but with the velocity equation. And then we're assuming that acceleration holds constant throughout the word problem. It's not always true, but for this level of physics, that's usually good enough. Alrighty, I hope you liked the Think Like an Expert tutorial. Hopefully that helps you walk through motion graphs if you're having a hard time understanding those. Bye.